Okay, so we continue. This is page 69. And this is the part B. In part B, we use the new theory. So let us perform the iteration of the double Wiener Ito integral. And then we have discovered the link between Ito's theory of multiple Wiener-Ito integral and our new theory. Okay, so here we integrate from A to B, or for f, the integrand is fs gt. This is the integrand. This is the integrand. And we integrate this integrand first with s variable. And then after that, this is the integrand. And we integrate this new integrand in bt. What is this? So we perform the iterated integral. And let's find out what it is. Now the integrand, this is the integrand, which is a random variable. And this random variable is, in general, is not adapted. And so this integral is not going to be Ito integral. It will be our new integral. You see, that is the whole point. But to put this in our new theory, we need to decompose the integrand into some of stochastic processes in terms of adapted part, or the Ito part, and the counterpart, namely the instantly independent stochastic processes. So how do we do that? We need to decompose the integrand. So the integrand is this run out of pen ran out of the ink. Okay, so this we need to decompose the integrand. So the integral from A to B of f s gt. Oh, I'm sorry, SG. First, we write this integral from A to B. This is integral in S, so we can bring gt out. bring gt out, and the integral from a to b of fs dbs, and then dbt. So we need to find this integral. And the decomposition is for this integral. Gt is a deterministic function, so it's of course is in the intersection of adaptive part and instantly independent part. Okay, the pen is getting difficult for me. So the decomposition is this. The integral from a to b of f s dbs equals to the integral from a to t f s dbs plus the integral from t to b of fs dbs. This is the decomposition. This part, you see, this f is a deterministic function. The first part is when the integral is adapted. And the second part here, when you write it as the limit of the Riemann-like sum, it has the increment of the Brownian motion bs from t to b. And so this is instantly independent. And therefore, this integral is defined in our new theorem. And I will do this in the next page. Okay, so this is page 70. So this is here from the previous page. Therefore, we have the integral from a to b of gt, the integral from a to b of fs dbs dbt. This equals to the integral from a to b of gt, and then the integral from a to t fs dbs plus the integral from t to b of fs dbs. And then dbt. So this is Ito part. And this is the counterpart. And of course, because g is a deterministic function, g multiplied by this Ito part is also an Ito part, and gt times the second integral is also instantly independent. Therefore, by our definition, this integral is the limit of the following thing. So instead of writing the limit, I just use approximately equal to that. Okay, it is the summation I from 1 to n. And then the for the integrand g, since g is a deterministic function, you see here a to b, t sub I minus 1, t sub I in this subinterval. The evaluation for gt can be taken any point in this subinterval. And so in particular, we can take g at the left end point. And then the important thing is here. For the first term, is the integral from a to t sub I minus 1. And then this is the second term is t sub I to b, and then Brownian-Motion increment. And then this is summation I from 1 to n. And then g t sub I minus 1 times here. For this integral now, we write this sum as the integral from a to b of f s dbs. Oh, excuse me for a second. Okay. And then we have to subtract the integral from t sub I minus 1 to t sub I of fs dbs. So namely, inside the parentheses, this is that. And then the Brownian-Motion increment. And now let's see what is happening. Here's the sum is over the first term and the second term here. So we split the summation into this sum and this. Now for the first sum, this, I cover this. And look at what is the summation sum. You see, for this sum, we can bring f out and then sum g. So it is the integral from a to b, fs dbs, times the summation I from 1 to n of g t sub I minus 1, the Brownian-Motion increment here. It is this. And then the second summation is, there's a minus here, summation I from 1 to n of g t sub I minus 1. Okay, and now I'm, for this term here, because of that, I put this almost equal to this, namely, this part here is almost equal to f. In this small interval, we can evaluate f at here ti minus 1. And then the increment here, this is the Brownian-Motion increment. Okay, so minus the second sum is this, g and then f, t sub I minus 1. And then the Brownian-Motion increment, t sub I square. You see this and times this. And therefore, this is almost equal to, now, this sum is the integral from a to b, the Wiener integral, gt dbt. And then we have the first one. Minus, now this part is almost equal to delta t sub I. And therefore, the second summation is the integral from a to b of ft g t dt. And we go to the next page. Okay, it is page 71. And hence, we have shown that this iterative integral a to b of f s g t db s first dbt. So this is an iterative integral, and this we have computed from the previous page. It is the integral from a to b of f s dbs times the integral from a to b of gt dbt, and then minus the integral from a to b of ft gt dt. And obviously, you see, if we integrate dbt first and then dbs, we get the same result. That is obvious. Now, from part A and B, we see that, let's see this, part B, okay. Okay. Part B is from this. And part A is from this. So you see, let's compare. This is from part B, this is from part A. The right-hand side are the same. And the left-hand side, this is double Wiener integral, and this is an iterative integral. And so from part A and part B, we conclude that the double Wiener integral is the same thing as the iterative integral. fs gt. So integrate s first from a to b, and then integrate from a to b, or dbs. So we have to conclude this. Namely, we can perform iterative integral for the double winner-Ito integral. So that is the message. And this video again is too long, so I stop here.